Dear organizing committee members and conference participants, it's a great honor to participate in ICAE 2020. I'm Zekai Mu from Nanjing University of Aeronautics and Astronautics, and I'm very glad to give my presentation named Axial and Radial Graded Porous Nickel Foam Catalyst for highly efficient solar-driven carbon dioxide reforming of methane. I will introduce my work from the following aspects. First is the research background and significance. Since the first industrial revolution, the repeat consumption of fossil fuels leads to the global carbon emissions have continued to rise by over 3,600 times, which is the primary cause of environmental pollution, energy shortage, and global warming. Thus, the conversion of carbon dioxide into high-energy fuels by renewable sources of energy is quite essential for the need to replace fossil fuels. There are abundant resources in solar energy in the world, which equals 5.9 plus 10 to the 6 power tons of standard coal a year. Among various carbon dioxide conversion technologies, by converting two powerful greenhouse gases, methane and carbon dioxide, into high-valued added fuels, carbon monoxide and hydrogen. The carbon dioxide reforming of methane, we call it CRM, by solar energy is a promising method to provide a sustainable and carbon neutral route for the storage of renewable energy. We call it three birds with one stone because the greenhouse gases reduction, solar energy storage, and chemical fuels preparation could be achieved by solar-driven CRM at the same time. Unlike the large pressure drop and the low thermal conductivity of powder catalyst, metal foam is chosen as the catalyst support due to its favorable optical depth, good thermal conductivity, wear plasticity, high gas permeability, and excellent mechanical strength. The second part is the introduction of numerical optimized model. Solar-driven CO2 reforming of methane on the porous foam catalyst is a complex physical and chemical process. It contains multi-scale and multi-physics and interdisciplinary studies. Here, a physical simulation model of coupling chemical reaction, porous media flow, fluid to solid heat transfer, solar radiation transmission and absorption is built. Further, by combining the CFD with GA, the optimized structure of axial and radial graded porous forms are obtained. The next come to the third part, results and discussion. We first built an experimental test system consisting of the mass flow meter, reactor, solar simulator, and gas chromatography to test the samples. Then we got the nickel-based catalyst supported on the nickel form. Because of the high thermal conductivity of the form, the temperature unevenness is significantly reduced by 84.3% compared to the powder sample. As a result, there is a significant reduction of agglomeration from 80.56 nanometer of powder samples to 21.09 nanometers of foam samples, which caused the carbon deposition is reduced by 38.5% at the same time. The solar to foam conversion efficiency reaches 36.5% of the foam samples, and it continuously operates for 28.5 hours with significantly improved stability. After checking the correctness of the model, the optimization of homogeneous porous nickel foam catalyst is implemented. As the result was seen in the figures, we can draw that the following conclusions. First, small pore size and porosity enhance the solar energy absorption and fluid to solid heat transfer. High porosity contributes to the reaction rates. The best optimization structure occurs with a pore size of 1.72 mm and a porosity of 0.93. When the light to foam efficiency, CO2 and CH4 conversion rates are up to 46.47, 89.53 and 83.55% respectively. Then the optimization of graded porous nickel foam catalyst is carried out. The pore size is defined as a function of its position. As we can see from the table, three kinds of structures are listed. Structures 1 and 2 are the optimization results of graded porous foam, and structure 3 is the best homogeneous porous foam. In the axial direction, the inlet pore size are larger for deeper solar radiation transmission. In the radial direction, the grid pore size show disparate light absorption strategies for better adaptation to the concentrated solar energy. After analysis of the fluid temperature distribution of three results, it could be found that the structure 1 and 2 show deeper radiative heating and better fluid to solid heat transfer capacity in the second half due to the progressive pole size in the axial direction. Structure 1 has a smaller pole size in the center area, which contributes to stronger solar energy absorption and fluid to solid heat transfer, and leads to a higher temperature and a more vigorous reaction at the center. Conversely, for structure 2, the large-sized pole in the center area further allowed the radiation to permanent deeper in the porous form and be gradually absorbed. The light to for efficiency of structures 1 and 2 are up to 55% and 52.2% respectively, and both higher than the 46.5% of homogeneous nickel form catalyst. Finally is the further research directions of us. We are working on the automatic generation of porous form model based on the three-period minimal surface theory. By solving the level set equation, we get the model of axial and radial graded porous nickel forms for further manufacturing by 3D printing. This work could be a new route to design and manufacturing of the efficient porous form catalyst for better adaptation to uneven distributed solar-driven CRM reactions. Thank you for your listening and looking forward to your constructive suggestions.